in this context, I'll just tell you what it turns out to be. So it turns out to be 2x plus 3y minus 4. And you get this. This is from, this is f of x naught, y naught, plus partial derivative at that point, x minus x naught, plus partial y, x naught, y naught, y minus y naught. Gives you that. Then, what you do is you show that the limit as x and y approach x naught, y naught of f of xy minus the linearization over the distance between xy and x naught, y naught is equal to 0. So it's an upper limit finding problem where this definition comes into play. So the challenge, one of the challenges, is finding the right algebraic manipulations to show that this actually does happen. And fortunately, I actually do have a general technique that I can show you. It should work for just about any problem. Well, actually, I confirmed that it works for this one, the one you're given. If we write out what it is we want to take the limit of, see, it's not going to be clean this time. Yeah. It doesn't help that I use my fingers as an eraser, so sheer laziness. So we want limit as xy approaches 1, 1 of our function minus linearization, minus 2x minus 3y plus 4 over the distance between xy and 1, 1. So that's what we're actually having to take the limit of. Now, you might be thinking, how in the world are you going to show, because based on what we did in the previous problem, you need to bound this expression, minus 0, in terms of square root of x minus 1 squared plus y minus 1 squared. So, I think, how in the world are you going to do that? Because here we have various powers of x and y, but you want to rewrite this in terms of x minus 1 and y minus 1. That's what would make the whole process a bit easier. The way you handle that is, well, trickery. It's not the only way to do it, but this will work. It's a little tedious, but it's effective. So, it's the numerator that's the problem. You want to write this in terms of x minus 1 and y minus 1, so that you can try the algebraic techniques from a previous problem. Because that one, everything was simple, everything was 0, 0. So, in here, we rewrite x as x minus 1 plus 1. Same thing for y. So whatever x and y values you're approaching, you're going to rewrite it this way. And then, once you substitute those in here, especially where you have powers of x and y, we'll multiply it out in such a way that you preserve the x minus 1 and y minus 1 factors. So I'll show you what I mean by that. So this whole thing is, I'll just do the numerator. So we'll have x minus 1 plus 1 squared, y minus 1 plus 1 cubed, minus 2, x minus 1 plus 1, minus 3, y minus 1 plus 1, plus 4. This is where things are going to get a little messy. So to square this part, so we're going to get x minus 1 squared plus 2 times 1 times x minus 1 plus 1. And then we cube this part. It's going to get even uglier. Y minus 1 cubed plus 3 y minus 1 squared plus 3 y minus 1 plus 1. And then we have minus 2 x minus 1 minus 2 minus 3 y minus 1 minus 3 plus 4. So now everything's written in terms of x minus 1 and y minus 1. Just to make the writing simpler, I'm going to change variables here so it's a little less cluttered. I'm going to let z equal x minus 1. I'll let w be equal to y minus 1. The problem is in terms of z and w going to 0, 0, so we're in the same situation as the previous problem. Limit as z and w go to 0, 0 of z squared plus 2z plus 1, w cubed plus 3w squared plus 3w plus 1 minus 2z minus 2 minus 3w minus 3 plus 4 over square root of z squared plus w squared goes to 0. I'm going to combine these constants. We have minus 2, minus 3, and plus 4, so it gives us minus 1. Z minus 3w minus 1. Now, if we expand this out, one thing that's going to happen is that all these terms over here are going to cancel. You can see that there's a 2z, which will be multiplied by a 1, a 3w that gets multiplied by a 1, and then 2 1s that get multiplied together. That will cancel. All of these guys are going away. So what we're left with is Okay, so then we cancel what we can. Gone, 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 and gone. Keeping in mind that w and z are both going to 0. The power in the denominator is effectively 1, because we have z squared plus w squared, but we're taking a square root. Notice that every term that's degree 1 or less cancel out. So this indicates why this is actually going to why this is actually going to 0. So then what you can do is take each of these terms over square root of z squared plus w squared and come up with a bound. I'm going to distribute here. I'll break up a fraction. So we have, I won't go any further than this. I'm just going to illustrate the idea. So let's take a look at this term, for instance. So what I'll do is I'll factor out, I'll take z squared and w squared and set it aside. So we have z squared w squared over w, z squared plus w squared. So this is less than or equal to 1, plus 3 z squared w, w over square root of z squared plus w squared. All that is less than or equal to 1. And we continue this with all the rest of these terms. We always have at least one factor of z or w put up top here to get something that's less than or equal to 1, so that way the denominator doesn't pose any problem. And then we're always going to have at least one factor of z or w left out here to give us something that makes us believe this whole thing is going to be less than or equal to, that's actually going to go to 0. So if we do this with all of the terms involved, then I'll go ahead and write out the result. In absolute value, the absolute value of this whole mess is going to be less than or equal to z squared w squared. Okay, don't do the absolute value there. Plus 3 z squared w plus 3 z squared z. So all I'm doing is that I'm taking one factor of w or z out. It doesn't really matter which. W plus 6 zw plus 6z plus w squared plus 3w, and that's it.
You only take like one degree of z or w?
Yeah, because one factor gets put up top here to get something, say, oh, that's less than or equal to 1.
What about like that 2zw cubed?
So,
like when you factor.
This one over here. Yeah, so I took a factor of w and set it aside over here. So that means this whole thing is bound. So this whole term is bounded by z squared, absolute value z squared w squared. It's basically just to get the denominator out of the picture. We still want to bound this in terms of some function of square root of z squared plus w squared, whatever function might happen to be. So here's what we can do. The highest power that we have in any of these terms is to the fourth. So for instance, this whole thing is less than or equal to square root of z squared plus w squared, all raised to the fourth power. Only because of these relationships. So then if we do all that, I'm going to make an abbreviation here. Let's let r be equal to square root of z squared plus w squared. So what we get is 6r plus r squared plus 3r. There's a lot of terms we can combine here. So what we get is r to the fourth plus 3r cubed plus 1, 2, 3, 4, 5, 12r squared plus 10r. So what you can do, again, it's a very crude bound here. We could say that this is bounded by, we add all the coefficients, 1 plus 3 is 4, 12, 16, 26, r to the fourth. Wait a minute. It's obviously true if r is greater than or equal to 1, but when r is less than 1, it's actually this term that becomes dominant. What you could do is choose an even larger constant. There's always a constant you can choose that is going to be big enough. And you can choose it to